This is an introduction to agent-based modeling. In the text, it'll be referred to as ABM a couple of times. So just not to confuse you, ABM is equivalent to agent-based modeling. Oh, okay. So what is agent-based modeling? Agent-based modeling is a methodology that is used to build formal models of real-world systems. So to parse this out, a formal model is a precise statement of components to be used and the relationships among them. And that pretty much is, we have these rules we designate, and everything in the system has to abide by those rules. But there are no constraints on like how relaxed those rules are or strict. So formal models is a pretty general term, equations, they're used in math a lot. That all kind of falls under that. So one of the distinct features of agent-based modeling is these systems that we're trying to model are made up of individual units. And so, for example, these could be atoms, cells, animals, humans, institutions, or essentially it can be anything. And in ABM, these individual units or agents repeatedly interact among themselves and with the environment in which they live in. And so here's my wee picture, people mulling about, and that kind of gives you like a representation of, this is just one example, but yeah. So the essence of agent-based modeling. So as humans have tried to do forever, we've tried to rigorously model nature in order to make fairly accurate predictions or estimations. And so we also, while also doing that, we also want to try to understand how these things interact together. And so what agent-based modeling, how it's different from other formal model methodologies, and by other formal methodologies, I mean, it's a pretty general term, but maybe a different formal methodology would be like equation-based modeling, where we have like an equation of numbers and each one describes some variable and they have different weights to like describe how strong preferences are for those variables. So if you've taken like a regression class or machine learning, as even those are more fall under like equation-based modeling. So the defining feature of the ABM approach is that it establishes this direct and explicit correspondence between, first, the individual units and the target system. So this target system is like what we're trying to model, and the parts of the model that represent these units. And then also between the interactions of these individual units in the target systems and the interactions of the corresponding agents in the model. So understanding what I just said with a picture always helps. So when we talk about direct and explicit correspondence between the target system's units, the people on the left here in the real world, and the agents in our model, these figures on the right, we mean we don't reduce the dimensionality of the nature we're trying to model. And so we can see we have an agent for each person, and also the interactions between the people are directly represented in the model shown by those arrows. A byproduct of this is that agent-based modeling can be very complex. And so if the more complex it is, inference can become more intractable, which pretty much means that knowing why exactly something happened is sometimes hard to narrow down. But we make up for this by being more precise in what exactly is going on. And we'll soon see what benefits this will have. And those benefits, after all, are why some problems are related to using agent-based modeling as well, others, or instead of other methodologies. And so thus, to wrap up what we just talked about in ABM, the individual units of the real world system and the repeated interactions are explicitly and individually represented in the model. And beyond this, there are no further assumptions. And here's that kind of a similar picture. This one's kind of messier, but you can see how we've kind of taken, there we go. Taken this is supposed to represent the system that we're trying to model, nature, real life. And we're kind of putting it, and these interactions are made explicit in our model. So now we're going to go through a couple of the benefits of agent-based modeling. So the first is flexibility. And this means that principally we can make our model as complex as we wish. And as I said before, this can come at a cost of making it harder to analyze and understand. Second, related, is that it captures emergent phenomena as well. So emergent phenomena result from the interactions of individual beings or entities. And this means that the whole is more than the sum of its parts due to the interactions between the parts in the system. And finally, ABM provides a natural description of a system. So this means we can get as close as possible to the reality of the system we're attempting to model. So we're going to hone in on the benefit of that agent-based modeling has, and that it models emergent phenomena very well. And so as mentioned earlier, emergent phenomena can have properties that are decoupled from the properties of the parts. So that this pretty much means if we look at the individual properties of each part of a system, so like each agent has these properties that belong to them, and we add them all up, and we sum them up, that does not equate to the properties of the system. The properties of the system is more than that, because the agents interacting with each other create new properties that can be attributed to the system. And so pretty much said that there. And agent-based modeling by its nature is the canonical approach to modeling emergent phenomena. And then here we have a picture of like I think it's common in Netherlands, maybe, could be completely off. I know they're starlings, but they like fly around in this way that is like mathematically unique. And that's kind of like an emergent phenomenon, or an example of one. So when to use agent-based modeling for emergent phenomena? So firstly, if individual behavior is nonlinear and can instead be characterized by if-then rules or nonlinear coupling. And nonlinear coupling here means that, ignore that. Nonlinear coupling could be thought of as when the interactions or the respondents between, the environment and agents, or a pair of agents, are non-proportional. And so nonlinear coupling is the idea that interactions between individuals and then also the individual behavior is nonlinear. And that's harder, and then a byproduct of that is hard to predict with models and equations. Not with models, harder to predict through equation-based modeling. And it's not as reproducible. And so, secondly, if individual behavior exhibits memory, path dependence, or non-Markovian behavior. And so memory is pretty easy to understand, like the agents kind of like have this kind of, if the system you're trying to model, agents have some sort of like memory capacity. And then path dependence pretty much means that on which path an agent takes, the agent will make different decisions, so it's dependent on the path that it takes. And then non-Markovian means that the probability of going on each path is non-constant. So say an agent has a 50% chance of going on one route. This 50% changes through the course of time. And this is just a couple of natural emergent phenomenon. Nice little picture. So what is an agent? With the minion. So agents can be thought of as decision makers in our model. And they can represent humans, non-human, animals, institutions, firms, etc. Essentially whatever you want it to be. And they have this thing called, each agent has individually owned variables which describe their internal state. For example, say the agents were playing a game, this would be their strategy. What are they supposed to do in the environment that they live in? And so this reflects the idea of nonlinearity. Oh, sorry, never mind. They are also able to conduct certain computations or tasks. And then there's instructions that are sometimes called. And they're sometimes called decision rules or rules of behavior. And this reflects the idea of nonlinearity. The interaction in the model can affect how an agent acts, whether this interaction is with another agent or the environment itself. So theoretically, we could have a program where if two agents have some interaction and a byproduct of this interaction changes the environment, that environment could have an effect then on some other agent on somewhere else. So these instructions are sometimes called decision rules or rules of behavior, and they most often imply some kind of interaction, which is kind of the main theme. So this is the last slide. It's a little text heavy, so we're going to go through it one by one. It's kind of just examples of individually owned variables that we just talked about, and then the instructions. And so say like we're playing a game and each agent is a player in this game. One of the variables could be some strategy, and this could be like an if-then statement. If someone comes, like, if there's a certain amount of agents around them that does something, or they're alike, then they do this, whatever you want, essentially. And then there's a payoff, which is a number. It's like, this can be how much benefit are they receiving from doing a certain action. And then there's a set of agents. The variable can be like my co-agents, my co-players, with whom the agent interacts with. And then a color, which can describe pretty much some characteristic of your choice. It can be an emotion. If someone's happy or sad, it can be like an affiliation. And then now we have examples of instructions. And so the first one could be like to play a certain game with the co-agents. I don't know why I said co-plagents. And set the payoff appropriately. The agents can update their own strategy. So you can be like, if this happens, update the strategy, and they have to revise their strategy according to the certain protocols that you've programmed. And then you think they can update their color, which we've said could be an emotion and affiliation. So there's a lot of flexibility in what they can do. And now I'm going to hand it off to Pinar to do a more bio-like part.
Yes, so hello. Did I introduce myself? I don't know. Yeah, thank you, Paul, for a great presentation. You can keep it on there, and you're unmuted. You're muted. Oh, okay. So today, this will kind of this is like a screenshot of what we're trying to create today. This is the interface tab of NetLogo. We'll be looking at a hypothetical tumor model. We're having a switch, so we're kind of alternating between two conditions when a person is a smoker or a non-smoker. And we'll try to reproduce this image, hopefully. Next slide, please. So just to give a brief background on stem cells and tumors and why they're interacting in my little interface. Stem cells are cells with potential to develop into many different types of cells in the body. So they're kind of the mother cell. Once they divide, as we'll see in the next slide, we'll have they have different modes of dividing, and they can either make a daughter stem cell or a differentiated cells that make up the muscle tissue, the skin, any kind of differentiated cell type you can think of. And as these cells divide, the DNA, the genetic material, has to replicate. And in the process of replication, it is definitely not perfect. There are a lot of mistakes that's being made as the genetic material is being copied to be passed on to the next cell. But the problem there is when you're a smoker, as we'll see in the next slide, bad things happen. But through mutation accumulation over time with these cells dividing, we see an uncontrolled cell division. So here in the picture, you see a primary tumor. So that's where the mother cell that decided to make bad cancerous babies, it's that it's called a primary tumor. And metastasis, so that's a benign tumor, it just stays there. But a benign tumor, if things go very bad with more and more mutation accumulation, the cell division goes out of control and they actually move through the bloodstream to a different region in the body, which is very bad for the individual, since it leads more unpredictable behavior of these cells, and it becomes harder to remove them from the body. Next slide, please. Yes, so the types of stem cell divisions that our agents are going to be cells, but some of them we are going to characterize them as stem cells, and some of them as just these differentiated cells. We'll call them transitory cells because they'll be kind of moving out of the mother cell. But stem cells can divide asymmetrically. So once they divide, they make one differentiated cell, which cannot go back to being a stem cell, although there's research that shows. I saw a question in the chat. At some point, does it become non-benign? For the cells that have metastasized, since it's in the mutations that have accumulated over time, that uncontrolled behavior is still in their genetic material. Unless there's like outside treatment done, it's very hard to control them. That's why once people get cancer, it just keeps, once it's becomes non-benign, it's becoming really hard to turn those cells back into being benign. But there's definitely research that's trying to reverse that process. But for our purposes, once it eats out, it eats out. So we'll be looking at asymmetric division, and one of our turtles, the stem cell turtle, will do asymmetric division. And we're also going to have these turtles also do symmetric division, where once they divide, they just make a bunch of differentiated cells.
Really quickly.
Yes.
Just to be clear, turtles in NetLogo are synonymous with agents. So they're like the individual unit of the model.
I apologize. We have not discussed that yet. Yes, agents as turtles is what I'm referring to. We'll get to that much more in detail. How common do stem cells become differentiated? So in development, once the embryo starts developing, we have the region where stem cells are stored. As the cells reproduce, they just become differentiated. There's no going back because of the molecular cues. So as you're born and the egg is fertilized, it keeps going on. But in a normal sense, unless you don't have any, we keep remaking a lot of cells. A lot of our cells die every day. I do not know the exact rate, but daily you lose a lot of cells, and that needs to be compensated for by either differentiated cells, and worst case scenario, the stem cells. But it's a really cool field. So next slide, please. So just to reiterate why we're looking at smoking and why I've kind of chosen to do this kind of a model, is that the smoke of tobacco contains these carcinogens that amplify these mutations. So as they enter the body, they go into the bloodstream, they enter these cells and really mess up the genetic composition and what's going on in terms of regulation within cells. So they cause cancer eventually. And cancer is so metastasis is once that primary tumor has these babies just popping off of there and becoming cancerous. So once they're in one place, we call them tumors, benign tumors. But once they show that unpredictable behavior, as you see in the picture, at the top left corner, there's only one. And then as the stages go on, you see more and more division into unpredictable regions in the body. So that's what I mean by cancerous. Cancerous ones are the ones that lead. But yeah, these mutations cause these cancer genes to turn on. And once they turn on, it's really hard to turn them back off because they really like invading the body. And with that, let's move on to the code. How about that? Was that good of a biological background? I think if there are any questions along the way, I'll definitely address those. I'll share my screen with the attendee version. I hope you guys are able to get the desktop on. So is everyone seeing my cursor here? Yes.
Yep.
Yep. Okay. So.
Oh, quick question, Pinar. So I just paste the attendee version into my notebook under the code tab, right? Or was I supposed to download it?
Yes. Yeah. Should I share the GitHub?
Yeah, if you just click the link, it should download the whole file, and it's like this whole project file instead of just the code.
Okay.
Good thing I asked. Thank you.
Yeah. Sorry about that. Should have clarified that in the beginning. So thumbs up. Is everything going good? Let me know if there are any problems. I'll just start with a basic overview of NetLogo before we get into the code. So this is the NetLogo window. We have three main tabs: the interface, the info, and the code. And here in the interface, we have our world, which is represented by this black box. And we have our command center, which I'll get to a bit more in detail later. But this is our world where in this world, we have these agents, as Paul mentioned. And these agents are either turtles, which move around within this world, or patches that stick to this world, make up this world, but they do not move. They can have changing properties. They have their own variables. They behave like individuals, but they do not move. What moves are the turtles. And we also have links and observers that are also called agents, but for today's purposes, those are the two main agents in the context of NetLogo that is applicable to models, the patches and the turtles. And so this is our interface bar, and then the info bar is basically the methods and abstract section of a research paper kind of. So at the top you have, why am I showing you this model? Why did I make this model? How it works, to kind of give some more detail into the context of what the model is trying to investigate and how to use it. So we'll be making these buttons hopefully in the interface, so what each button does, and extensions and credits. So I've also included the literature I used to get some of the values I did here. And we have the code. Also, do not mind this yellow bar. It's just because NetLogo has this wonderful check option where it checks your indentation and your syntax. So if it sees some like inconsistency, it warns you before you go onto interface. So it right now thinks that I have all these fill-in variables that are obviously not what we're going to use. And just to go back to the interface, just to make sure that everyone is working with the same settings here. When you go to the settings bar, it kind of controls the dimensions of the world. So the world is kind of set up as this, is made up of these quadrants. So we have the origin in the middle, and you can decide how just the overall dimensions of your world. And here I've just set it to 51 and 51, just based on testing out the code. But let me know if you guys have different values on there. I made sure to have it the same, but hopefully it works. World can wrap horizontally. So like Pac-Man, if the turtle leaves from one side, it'll just pop back in because it'll technically be a vertical cylinder, as NetLogo tells me here. Or we can have it wrap vertically, so it'll be a horizontal cylinder. If you turn both of those on, it'll be a torus. So it'll be like a donut where there's no escape from this. There's no boundaries. It's just a continuous world. But today we have both of those turned off, and hopefully everything is good with you guys' version. I'm looking at the same version, but just to make sure. Okay. And then we have these when you click this arrow here, NetLogo is great in that there's a lot of visual aspects that are just intuitively, you can intuitively just put them in there. And as you move along, you'll see if you decide to make your own models, you can utilize these in many ways. Today, we'll be using buttons, we'll be using a slider. Oh no, we won't be using a slider, we'll be using a switch. But sliders are for kind of having varying parameters. But today we have two conditions. The person is a smoker or a non-smoker. So it'll be a switch. You can plot things, you can monitor things, your turtles, your agents. You can monitor patches as well, since they're agents too. But this is the overall view. These ticks, so the NetLogo program, in NetLogo, time passes in discrete steps that are ticks. So, and NetLogo keeps track of these ticks. So you don't, unlike Python or, in a loop, you would keep track of this, variable I, and every time, you would have to manually keep track. But for NetLogo, it keeps track of the time itself. So in that way, it's really convenient for a lot of things. So with each tick command, the counter goes up by 1. So it's 1, 2, 3. Yep. So let's go to the code. So I hope if anyone has any questions about the interface, we shall move on. A last thing for the command center, I know it kind of looks sad and empty and kind of purposeless, but what the command center does is you can actually modify what your agents, your patches, your turtles are doing in the world through the command center. So you can choose to play with the turtles, you can choose to play with the patches. The observer is just a general, as an observer, you can go play with the turtles and the patches. But what this does, it does not touch your code. So whatever you write on here, it stays there. It does not change anything in your code. It's just to help you. We'll see once we get to create things. I'll give more examples there. So let's get started with the code, shall we? So now we want to pretend that this is one section of the human body, and we will have a stem cell, and it's baby stem cell initially. And we will have these two conditions, as I mentioned, smoker or non-smoker. And based on that, the cell division behavior will change. So like Python or other coding languages, we can have global variables. And with NetLogo, since turtles are their own kind of entity, they can have their own turtles' own variables. So here, we'll put in some variables that we want our turtles to keep track of themselves. So it's just in their context. Patches don't need to know this information. It's only for the turtles and how they modify their own behavior. So let's start with the variable to keep track of whether a turtle represents a stem cell or not. So as I mentioned, once they divide, they can become differentiated cells. And here we need to keep track of what's the daughter cell differentiated cell and what's that original stem cell. So let's say that we'll fill this out as together. We'll say stem and then question mark. So the question mark does not represent, the question mark is for our purposes. So we're questioning, are you a stem cell? Are you not a stem cell? And later on, we'll assign a Boolean, so true or false, to this variable to be checking if the cell is a stem cell or not. And we need a variable to keep track of the age. So cells are not immortal. They compete with each other. They have their abilities to use nutrition goes down. So they die eventually once they reach a certain age. So we need to keep track of their age. So let's say age for that one. And then we'll also want to keep track of metastasized cells. So we'll have one stationary region where the cells just keep dividing. They haven't reached the bloodstream. They haven't reached that mutation threshold to induce them to go to other regions. So we'll call that metastatic question mark. I hope that was good spelling. Yes. So is everything good? on everyone's part? Okay. So now those are what the turtles will want to keep track of. But then now we have the global. So here we want to keep track of the number of cells we have. That also affects competition among cells and the mutation. So as we keep making cells, we get more mutation accumulating in these cells. But let's say we'll keep track of those in cell count. So cell dash count. And for a variable to keep track of our mutation accumulation, we'll say mutation. Is that good? Yes. Okay. So now we have defined our variables for turtles and global. In NetLogo, I think you can do this with a lot of programs where you can kind of shrink. But if you guys think it looks busy up there, you can scroll or shrink that section. But let's move on to setup. So what's kind of always there in NetLogo? Oh, there's a chat. Okay. Oh, she left. Oh no. Okay. There's a setup and a go. So setup, kind of as it is in the name, it will set up the world for our agents to start interacting in. So for our setup, in NetLogo, when you want to create functions, as we would call them in Python, in NetLogo, you're kind of defining procedures. So rather than functions, they're called procedures. And to make a procedure, you say to, and then you name that procedure. So here in our case, it will be setup. To setup, so we're setting up something, and each procedure ends with end. So you have to end the procedure. What goes right after the setup is clear all. This must be there because every time you call setup, you want to be setting up your world, but you don't want the previous stuff, the previous simulation to be there. So you have to clear everything. This is a primitive, it's built in to NetLogo. You do not have to define this. It clears everything. And we want to, in our setup, so normally turtles, as the name suggests, they first show up as arrows-ish, like on default, but then for them to look like cells, we want to make them into circles. So this is also another primitive command. It says set default shape of turtles. So you first put in what you want to change the shape of. This could be patches, and then you write the shape. So this is a format that NetLogo recognizes. Okay, it should be a circle. So we'll move on from there. And so we want to now color our patches in the setup. So now we change the shape of our turtles. We want to color the patches. And to make things happen in NetLogo, to talk to the agents, you have to ask them. You have to be nice to them. You have to be polite and say, ask patches. Patches are also agents. So we ask them to, so once you've asked something, to the part of the code where you tell them what you're asking for, you put a bracket, you open a bracket, and here we'll say set your color. So okay, let's say, okay, set color, and then white. White is also recognized by NetLogo. But there's a problem here. Color is used by the turtles, but we have to differentiate between what the patches have and what the turtles have, right? So for patches, we put a P. So set P color, patch color white. So in our setup, we've set our color world into a white blank canvas. And then we're going to create our stem cells now. So to create stem cells, it will be kind of a larger procedure. So here we'll just name the later procedure we're going to use. So we'll call that SetStem. And then we'll define that here. But we want to be calling this procedure every time we set up. So please put the stem cells in the setup version. And we're going to now also put another procedure that we'll be naming later. Is called evaluate parameters, which we'll call them evaluate params. If no cells are alive, we need to stop the program. Everyone is dead. So with every setup, we should check if there's anything left alive. There shouldn't be. So just call that in there just in case. And then we will reset the ticks because, as I said before, we don't want the accumulated time frame in there. So that was the setup. And now let's move on to this procedure I named SetStem. So a function, a procedure, function/procedure. So in Python, it would be a function, but here it's mostly called procedures. So we'll say to SetStem. You can't type. SetStem. We want NetLogo to create 2 turtles. So for our purposes, we're kind of skipping the step where the mother stem cell differentiates into that asymmetric stem cell differentiated cell. We're kind of already creating those 2 stem cells and assuming one of them is the daughter cell that will later on go on to metastasize. But here, so right now we're creating 2 stem cells. And NetLogo is very intuitive in terms of asking things, create turtles. So we're literally asking the program to create 2 agents, 2 turtles, and we say 2, how many you want. And then we open the brackets because we want these turtles to be doing things. First of all, we want them to set their size to 2, and then set their initial coordinates into, I will not go into detail about where this is because it will take long to kind of go through where the PX core, and, but this is a location as we'll see in the setup version. But basically the first part is the X coordinate and this is the Y coordinate. And we'll ask them to set their color. As you see, there's no P here because this is not a patch. We're asking turtles to do things now, and we've just created them, so we don't have to ask them separately. They're created and they have to do these things, and then set their color blue. Now, here are initial conditions. So we're still in the setup. We want our newly born stem cells to abide by these rules, okay? So we want them to be stem cells. So we will ask them to set themselves stem question mark as we had here to keep track of whether they're stem cell or not. We'll set that to true. So we're telling them once you're born, once I hit that setup, you're a stem cell, and those 2 first stem cells. And next, we want them to set their metastatic property to false. So they have not metastasized yet because we need that mutation accumulation happening for that to become true. So we'll say metastatic question mark, and then we'll say false. So you're not born as a metastatic stem cell. You're still normal. And we'll set their age to 0 because this is set up. This is just, the initial condition. They're kind of just born. And one thing with NetLogo is if you do not specify a lot of what the variables, if they're numerical, it'll just assume it's 0, but we'll just write that it's 0. And then we'll set their mutation accumulation, the initial at least, to 0. So we're starting from this baseline. You're a stem cell, you're not metastatic, your age is 0, you have no mutation relative to what's about to come. Obviously, they have mutations biologically, but we won't be recording that. Okay, so everything good so far? So we've set
the mutation one is a global variable. So are they interacting with that global variable, each one of them?
Yes, they have access to it.
Cool.
So great question. Thank you. Forgot to mention. And then we have, so we're now out of our creation of turtles. Now we're assuming we have these 2 turtles since the code will start calling everything by line. In NetLogo, once you've created turtles, they have their own individual numbers. So the first turtle to be created is turtle 0, and the second turtle to be created is turtle 1, and then 2, 3, 4. So when we ask turtle 1, I'm assuming that's going to be the daughter cell that came out of the asymmetric division. So the mother cell is kind of the 0 in our case, but I want turtle 1, the baby cell that will metastasize, that will leave that area, to head itself to 90 degrees from that quadrant. So assuming it's looking that way, just head that way when I tell you to move. It's not moving right now, but set your head to that direction. So that's what this is. I didn't want to, yeah. But, and then we'll set our initial cell count because we have to keep track of our cells. We'll set cell count to 2. So we've created 2 turtles. We have 2 cells. This is the setup. And what else did we have? We had evaluate parameters. So now we're done with the SetStem procedure here. I'll maybe minimize that for now. And we'll put in our evaluate params here. And in NetLogo, wherever you make a procedure, NetLogo finds it. There, you don't have to worry about defining a function or procedure before it's called. NetLogo goes through it, and if it sees it, it'll just call it there. There's no limitation. So we're evaluating parameters. I want to store the cell counts in one variable as I've defined here. So I want to now set, work with the cell count. So I will set the cell count to, once I'm evaluating the count, how many turtles are there? So we'll use the cell count in our evaluation later. So I want NetLogo to see how many turtles exist. Once a turtle dies, it just disappears from the count intuitively. So once it's 0, that means there's none alive. So I'm saying set the cell count to how many turtles there are. This is also a primitive command in NetLogo. And then our condition is, so we want the program to stop, right? So we have to have a condition. So if parentheses, open parentheses, if the cell count is less than or equal to 0, close parentheses, please, now we have our condition here. And then if this is true, please execute the following thing within the bracket. Please stop. When you, oh, we have indentation. Let's go. Okay. Once whatever you put in brackets, if this is true, it'll stop. If it's not true, it'll just not do whatever is in this bracket. So as we said, if all turtles are dead, please stop. So now we have our setup. That took a bit longer than I expected, but I think we'll now create our first button, which is the setup button, because we have everything we need to be able to set up our world. Let's go to the interface. And to make buttons, you click on button, and then you just click on a random location within this white space. So when it says commands, it's asking me, what procedure do you want me to call? And I'll say, please call setup. And it'll automatically become the name, but you can also change the display name, but it's usually kept as setup. So I'll click OK. So now it's telling me that there's nothing named setup that has been defined. And I am questioning why. Oh, yes, we also have to make our go button. Let's check our code, make sure. Okay, we're still in the fill-in one. Okay, now we'll move on to go. Okay, since go is shorter, we'll quickly go through that if we can't get done in time. But let's make our go procedure. So we want to ask turtles once I click go. So go is what's doing the simulation. And I want to ask my turtles to do the following. Since they're my agents, they're the things that are moving around. They should have some change in behavior. So we will have a switch that will be called leave trail. What it basically is, as you move, leave a trail behind you. So it'll be a, you'll see a line. I think I showed in the PowerPoint. So we say if else. So in Python, you write if and then you write else in a different step. But in NetLogo, you write if else in the beginning. So if it's true, if the condition is true, it'll execute the first bracket. If not, if else, it'll execute the next bracket. So if else, we're still in the leaf trail one, but the leaf trail switch is open. So we'll make a switch really quick. So if the leaf trail switch is open, please pen down. Pen down means leave a trail, have like a pen that's following you. And if it's pen up, there's nothing behind you. There's no trail. So we can quickly make a button. Making a button also, making a switch makes a global variable. So you do not have to declare that there's this thing called leaf trail within the code. You can put it here. So leaf trail question mark. Okay. So this is leaf trail. It's defined within the interface. I do not have to put it in my globals or anything. By the creation of the switch, it's just in the program. So now I want my turtles to, if they become metastatic, which we'll discuss if we have time later, I want them to move, right? So if I want them to move, they have to follow these conditions. So if right now I'm looking at the cell, the stem cell that was born out of the mother, if you are turtle 1, who is asking the turtle which turtle you are? So if you are turtle number 1, and your x coordinate is on, which we'll see, wait, why can't I, okay, on this side of, if you're still on this side of the world, which is why this is set up this way, please become metastatic once the conditions are allowed. So and if, okay, sorry, if you're turtle number 1 and your x coordinate is that, and so you're on the left side, you haven't left the mother group, and your metastatic is true, which will become true later when we accumulate the mutation. If that is also true, please forward 8, go 8 steps, go 8 patches, and that's it. That's all I'm asking the turtle to do if it satisfies these conditions. And now we'll increase with every go, with every simulation. So think of each go happening as one tick. With every go, I want to set my age, set age to age +1. So after so this NetLogo sees this and this part as 2 different declarations. So I'm telling it to set its age to directly whatever comes second. So with each go, the cells are getting older. So now here we're just going to write the names of our functions that we would have hopefully named down below. But for the accumulation of the mutations, we'll call it accumulate mutation. And then for metastasis, so when it does happen, metastasis, yes. And for the daughter cells, the transitional cells, so differentiated cells, to move, we'll have a function that's called move transitional cells. And then for mitosis, so mitosis is constantly happening. It's the action of these cells dividing. So we'll call mitosis with the go function. And each of these procedures, functions have conditions within them that need to be satisfied. So even if I call them here, if the condition is not satisfied, it's not gonna metastasize. Calling it here does not make it so that I'm telling every cell to metastasize. They have different conditions as the code down below has. Will I get to? Will I ever? Okay, and then death. So if the conditions for death is satisfied, please die. Sounds mean, but at the end of everything, we want to have our tick kind of increase by 1. So with each tick, as I mentioned, the counter goes up by 1. And I do not have to say tick +1. I just need it to tick. And we're evaluating parameters here as well. So as the code is running, I want to keep track of whether any cells are dead or not. So let's go to the interface again. So this was our go function. We asked turtles to do things and call these procedures that will each have their own conditions and tick and evaluate as parameters. Let's go to the interface. Let's add a button that says go. And its display name is go. So for go, usually we keep forever open. If you do not click forever, what you do is, if forever is off, once you click go, it just runs the code one time and it stops. It wants you to click go again. So if you click forever, it's where the simulation part comes on. So you do not have to be manually asking NetLogo to keep ticking. So we'll say go. I will place this here. Let me see. Why has nothing called go have been defined, even though I have defined it? Okay. Technical difficulties.
Is it angry that we still have like some things not defined, like the different functions not defined?
Yeah, probably. Yeah. If I try to kind of comment these out, let me see if I can. No. Control. Okay. Let me see if that makes. I apologize. Are we out of time, or is it me?
Yeah, well, if anyone has to go, you have to go. But I'm kind of willing to stick around. I'm having fun with it, and I kind of want to see it getting working. So, Bernard, if you're okay,
Yeah.
I'd be fine sticking around a little bit longer and continue to mess around with it.
Yeah, if anyone has to leave, please do not hesitate. We respect everyone's time. Please don't feel bad. You can really leave. It's okay. Also, water break. Sorry. Okay. So sorry. I think my brain just needs nutrition right now. It's really not there. I tried this before.
Why don't we define mutation, metastasis, and death, and we can skip the treatment bit, but we can kind of move relatively quickly and see if it starts working. Then at that point, I think maybe it's angry that some things aren't defined.
Yeah, because we do have our setup, and if it's in the procedures, it means it is something defined. I'm just questioning if I'm doing something wrong here. No. Let's observe. Okay. Let's keep moving now. Mutation accumulation. So as I named it here, accumulate mutations. I have to use the same name, accumulate mutation. So in this function, it is to, based on being a smoker or non-smoker, there's going to be a different math that goes into the percentage of how much you're getting closer to that metastasis mutation threshold. But here, I just basically said with every 10 cell being present, with every 10 new turtle, cell count, as you guys remember, is counting the turtles basically. With every cell count, so here we have our smoker switch. So the two different mutation conditions depend on the person being a smoker or not. So smoker ? We did not have to define that here because that's also going to be a switch of its own. As I mentioned, once you make a switch, you declare that variable within the interface and it translates onto the code. So smoker ? Yeah, the code is just really mad that we have a bunch of fill-ins. So this is the math. I've already kind of put it in there so we don't lose time. But we're asking the mutations to keep increasing with however cells there are, divided by 10 times the incidence rate. But we can, if anyone has any questions, but we can move pretty quickly over there. So it's saying if you're a smoker, you have a higher percentage of increase with each tick. If you're not non-smoker, you have much lower incidence. So after accumulating our mutations, we're going to our metastasis. With metastasis, here we want the following conditions for turtle 1. So remember, turtle 1 is the baby stem cell. We're asking turtle 1, if your mutation, so as we keep setting the mutations, and remember the mutation, the turtles can also access mutation because it's a global. If your mutation is greater than or equal to 30, which is kind of the 30% threshold for metastasis, please, and you're not metastatic yet, so you're not, you're still in that mother group. Metastatic, question mark, goes false. So you're not metastatic. If your mutation is over the threshold and you're not metastatic, please set your metastatic. So you will now metastasize. You will leave the mother group and go on to other tissues. So set metastatic, question mark, to true. So now with this procedure, we made our turtle 1 into a metastatic cell type. And with that, that's not going to be the only cell moving. It will make more of itself. So those will be the transitional cells. Those are not stem cells. So we're telling, if you're not a stem cell, if not stem. So not is like kind of if stem is false, if you're not stem, open bracket. This is setting your color as you age. So this number multiplied by age, as NetLogo's color scale works by numbers. So as numbers on the scale gets from 0 to 100, as it gets closer to 100, it goes to white, and darker colors are near 0. So as they kind of die off, we want them to be lighter colors to have some kind of gradient. And please move forward by 1. So if you're not a stem cell, please move on, set your color to this thing, this range, and move. And then we have our if you are a stem cell, if you are that second daughter, if you are that mother stem cell, so by not saying true or false, we're telling NetLogo to assume this is true. If stem, please hatch. So hatch is when a turtle makes one more of itself. So hatch 1 means the turtle makes one more of itself. So hatch by 1. And since the go procedure will keep going simultaneously forever until I stop it, it'll keep hatching. So this is not just saying it to make one baby. It'll continuously make babies until they get old and die. And then rotate 360. So just find a random number from 0 to 360 and rotate yourself to that direction and move forward 1. That's what I'm saying to these cells. So this is the movement of the differentiated daughter cells. So now we have mitosis. And I think I made a mistake here. If your age is less than 6, please continue to do the following, because as you get old, these cells won't be able to make more of themselves. So while their age is less than 6, those cells should also keep dividing. Here with mitosis, I'm asking the stem cell to do mitosis. I apologize for that mix-up. Yeah, so here, transitional cells are not stem cells, and they need to make more of themselves as they move along, because they're also cells. They also divide. The stem cells are not the only thing that are dividing. So mitosis, if we are a stem cell, we're also asking them to hatch, go forward by 1, ask the hatched once, because as you see in the indentation, it's belonging to the newly born cell. And we're asking this newly born cell to become red. And since it's born out of the stem cell, so since we asked the stem cell to hatch, please set your stem. Since with every new cell creation hatching event, we need these cells to know whether or not they're stem cells or not. We only have 2 stem cells in each condition. The rest of them are just non-stem cells. So please set your stem cell property to false. And then we can move quickly through this part. This is just to set the new age for the metastasized turtle whose age is, who was 1, as I mentioned. So turtle 1 is that daughter stem cell. And please, if you're that, set your age to 16. And if you're not, you're newborn, set it to 0. So this was metastasis. I apologize for the confusion there. But let's move on. Hopefully we'll get some things to work, please. So now we're at death. We're close. We're close to the end. Victory, death. For conditions of death, we're asking non-stem. So what does non-stem mean? When you're not stem, question mark. Non-metastatic, so not metastatic, meaning you're not a stem cell, you're not one of those ones that left the mother group, you're one of the dividing cells around the mother stem cell. So it's still a tumor, but we're talking about those cells there. And if your age is over 10, so we're talking about natural death here, not based on any treatment yet. So once you go over the age of 10, you're old enough to die. It's kind of sad. And then we're asking them to die, which is very sad. One of the depressing commands in NetLogo. And now we're asking our we're with the not stem cells, non-stem cell. So we're saying if you're not a stem cell, but you have metastasized, so you're not a stem cell, but you've left the body and you're one of those dividing ones around the metastasized region. And then we'll say metastatic, question mark. And then these ones will die earlier because technically they're kind of away from, so once your age is over 8, which is a lower threshold than for what was in the primary tumor area, they have less of that nutrition that the original stem cell was dividing and creating a tumor in. So they kind of die earlier off. And since they're in a different tissue as well, the conditions are different. So we're asking them to die within these brackets. So if these conditions are true, execute this. But if they are not, just don't do anything. So as long as none of these are, we have the and telling, yes.
Yes, so is there any difference between stem question mark equals false and not stem in the conditions?
No, it's basically the same thing. Yeah, as you said, if stem question mark by itself is just, yeah, you are a stem cell. So it's, as you said, false or not are kind of similar things, but just to make the language easier, if not stem or if not metastatic. So it's kind of making that flow of not logic easier, hopefully. So now I'm checking my code. I was still mad about these. Okay, I'm going to comment these out really quick.
And to be clear, Dick, mass comment, you do, if you're on Windows,
yeah.
you do control semicolon, or if you're on Mac, you do command semicolon, just to get whole commented out.
Yes. Okay, yeah, they're not mad anymore, guys. Woo! Okay, please work. I shouldn't be like this. I'm so sorry. Let me see what else we need. Oh, we haven't done any treatments. So let's kind of make these look pretty, and we can move them around by just kind of highlighting them, and then just to have more coherent. Okay, please set up. Why? Oh, why not? It works for me. I thought it worked.
You know, I actually ran into this one. I should have mentioned this. I ran into this one at one point when I was messing with the lesson. And oh wait, maybe.
Okay,
oh, yeah,
just
circle 2 was defined and circle 1 was defined, but circle 3 for some reason wasn't. So you can, yeah, I think that works.
Interesting. Okay, yeah. If you guys can, if anyone's still following my messy code, if anyone can delete the 3, I think it works. We'll check our code. Everything looks good. So we've set up our world. As we said, it's white now. We have the initial 2 turtles, but you can't really see. Now command center comes in handy. We can ask the command center to inspect. Inspect means just give me more details about, let's say, turtle 0. Can you guys see this popped up window with the, okay, so what NetLogo has is okay, where did that go? Oh, properties. Sorry. What am I doing? Oh, I'm sorry. Because of the zoom like window, everything is moving around. Okay, so you can look at individual turtles. Right now, since both turtles 0 and 1 are in the same location, you're kind of seeing one blue dot. But if we said inspect turtle 1, it would show the same thing. But here you can see all the properties. And interestingly, you can see the ones within turtle's own. Remember, before the globals, we made a turtle's own. You can see STEM question mark here. You can see the age. You can see if it's metastatic. So it tells you all these properties, and you can look at this at any time in the simulation. So, oh my God, so exciting. Should we go? Should we click go? Please work. Oh my God. I get it now. With circle 3, it had a dot in it. So it made it, let's say circle 2. I'm kind of sad if we can't get the full experience. Set up, go. Oh, okay, that's ugly. Oh, I'm sorry. That was very bad. What's wrong with you? Please don't be uglier. You know what? I apologize, guys. Let's make it a circle. I won't be greedy. But here, right now, the smoker switch is off. The person is not a smoker. Leave trails is off. And you see the ticks. So the ticks keep going because I have not stopped the go. And once I do, ticks stop, simulation stops. What's happening here is you can make the simulation go slower, faster. Going faster really makes things, yeah, it's not pretty. But slower, you can kind of see more in detail. With faster, the discrete updates you see on the world is just like frame by frame. So like a lot of time has passed. You don't really see it go faster. It just becomes frame by frame. But once you make it go slower, you can actually, let's set up again. And as you just saw, the world becoming slowly black, from black to white, right? What NetLogo is doing there is I've cleared everything once I called setup. So it's actually a blank slate. It's empty. Once I recall setup, it starts filling in every single patch and starts making them white randomly. So that's kind of cool. And now let's open the trail. We're still at the non-smoker person. You can see more since I have my ticks go slowing. You see the lines, right? So what has been going on is, what did I do? I'm sorry. I clicked setup on accident. I was meaning to click go. What's happening is with every single cell that is dying, so I don't know if I can zoom in. Let's say go to turtle, inspect turtle. Probably by now, hundreds turtles might have been made. Okay, the 100th turtle has already died. So it's telling me it's a nobody. But as they die, you see it leaves the trail, but it's not there anymore. So you don't see a circle anymore. So you just see the line. So each line kind of represents a cell that was there, but has died. So let's do the exciting part, and I'll send you guys away. Let's open smoker. Let's set up again, have a clean. As I said, with smoker, we have a higher mutation accumulation happening with each 10 cell being produced, hatched. Let's say grow. Did you guys see that? You saw the blue. Let's make that slower. Okay, let's go way slow. Kind of watch that daughter stem cell move away, because remember we set its heading to 90 degrees. So once it said, okay, I'm metastatic now, through those conditions we created, it will yeet that way. I'm sorry for my language.
Now, would that happen if we let the non-smoker run for sufficiently long? Is it just because the accumulation rate is super, super low?
Yeah.
Okay.
It's because it's really low. And also also similar to what's happening in reality is that there's like carrying capacity for the tissue to, have, there can only be so many cells. With cells dying and reproducing, you kind of level off. So with my version of the code, unless you change around the age of death, you do not see that, but you can, as you said, since it's such a low number, you don't see it with my version. But yeah, with younger dying cells, that with the change in carrying capacity, that could have been possible. But we're still, oh my God, this is too slow. It's kind of, okay, wow, look at it go. And then it stops because I only told it to go forward 8 steps. And then now it has, imagine this has a different tissue, as I showed in the slide. It goes into the bloodstream and starts dividing in a new location. So this is very bad for the person. But yes, let me one last thing. Let's inspect turtle 1. So as you see, you cannot see turtle 0 because it's behind all of these red cells. It doesn't, NetLogo doesn't, take it out of there and, hand it to me on a silver plate. It's behind all those cells that are either dead or, they're, dividing from. But also, if you notice the color gradient, the newborn cells are red-ish, like they're more red. And as they leave, they kind of become pink. So that also has to do with the age code part we had. But yeah, I think I don't want to take you guys' time more than I have. I'm so glad it worked. I didn't want to leave you guys with like a non-working setup and go. As Emilio said, it probably had to do with all these procedures not having been there yet. But thank you so much for coming and listening to me. And if you want to do the treatment part on your own, it's definitely in the instructor version. I think the only problem we had was the circle. Hopefully, other than that, the treatment with the conditions here would work. But yes, we did it. Thank you so much for sticking out, and yay. I'll unshare. I'll stop share. Does anyone have any questions? Any last comments, feedback, anything? I'm open to.
Thank you so much, Pinar. That was a lot of fun. I'm glad that we got it working. It's fun to see things going, and it's nice with NetLogo that you have that nice like visual interface, because you don't need it for agent-based modeling. You can do it and just let it like run in the background, but it's really cool to get to see it working. Like that's one of the more fun parts of agent-based modeling.
Yeah,
you get to see it all just going,
Yep. Was that all good, Martha, for you? Did it work?
Yes, of course. It's very informative and it's very easy to set up.
Right. Okay, I'm glad. I mean, there's so many other, if you go onto the NetLogo website, there's so many models you can explore. There are tutorials that you can start from scratch, because I feel like, I hope I kind of gave an idea of what NetLogo can do for you. And you might just not remember, how to set up things, but there's always literature, there's the tutorials that really more slowly walk you through. I kind of tried to fit everything into this period, but I hope you continue on doing NetLogo because it's fun, right?
Yes, of course.
Yep. Thank you for coming. Thank you for coming.
Yeah,
Thank
thanks so
you.
much for coming, Martha.
Yeah, thank you so much for
Yep.
coming.
Yep.